Okay, so good afternoon, everyone, and welcome to our cyber training webinar. So this project is called Broadening the Adoption of Cyber Infrastructure and Research Workforce Development for Disaster Management. So this project was funded by National Science Foundation. And today, we are honored to have Dr. Zhuping Sheng from Department of Civil and Environmental Engineering at Morgan State University to give us a talk on the topic of improve highway safety by reducing the risks of landslides with a smart alert and warning system. So Dr. Zhuping Sheng is a professor in civil engineering at Morgan State University, and he is a registered professional engineer and certified professional hydrologist and a fellow of American Society of Civil Engineers. So he had over 40 years of research and practice experience in geomechanics and water resources engineering. And his teaching and research interests expand into enhancement of STEM program and applications of AI, and including the innovative technologies such as smart sensors and their application in identification, assessment, and monitoring of geohazards. So Dr. Sheng has served many roles in professional societies such as American Water Resources Association and American Institute of Hydrology. So before joining MSU, so he worked as a faculty at Texas A&M University and served as a center director at Texas A&M Agri-Life Research Center. So he received his PhD degree from the University of Nevada, and he has a Master of Science degree from University of Chinese Academy of Sciences, China, and a Bachelor of Engineering degree from Tongji University. So let's welcome Dr. Zhuping Sheng. So welcome and thank you for your time, Dr. Sheng. The floor is yours.
Thank you, Dr. Zhang. I'd like to thank the project team, Dr. Wang, Dr. Liu, too, for inviting me, even though I'm also serving in the project, for the opportunity to share what we are doing at Morgan State University in terms of geohazard mitigation and the prevention. That's just one of the aspects. We're also working on land subsidence and other geohazards, certainly flooding and so on. This project is funded by USDOT University Transportation Center. I'm going to explain a little bit more later. And also Maryland DOT or State Highway Administration. Thank you again. And I'd like to say hi to all who are online or in the classroom for attending. Let's see. All right. So here's the outline I'm going to cover for this talk. Try to highlight some of the research ongoing in terms of landslides and what potential approaches we might be able to detect earlier, try to prevent disasters before it happens. So early warning system and also detection would be one of the critical components for our future research. So what landslides? Landslides is the Earth's movement. I will show you different types. It can happen in your backyard. It can happen. You see the lower left side, it's apartment. was collapsed because of landslides. I have video there, but I'm not going to click it. It caused troubling in terms of presentation. On the right side, you can see it's in Maryland, 2024. It's along the highway. It certainly impacts the transportation. In some cases, it also totally half of the mountain can be collapsed. On the lower end, you can see in California, simply block the road. It certainly affects the community who are using this highway for their commute and transportation. So if there's a tourist, then tourism will be affected. On the right side, you can see that's the slides in Alaska that killed 5 members of the same family, just one slides. So it can cause economic impacts, and it can cause people's life. Annually, even though you don't see the big numbers, sometimes one event can kill, tens, hundreds. But on average, about 20 to 50 people may be killed by landslides. I think our more advanced monitoring, early warning that help to prevent some of the disasters. But still, it can happen. It can kill people and certainly cause direct economic losses, 1 to 2 billion a year. Indirect, cost can be several folders greater. Most slides are related to heavy rainfalls, storm event. So also the steep slope tend to have high potential for failures. Certainly geologic formation is a soil or is a rock. It can have different impacts on the slope stability. All right, here shows field types. You don't need to through everything, but look at here just shows some different types of potential failures you may observe when you drive along the highway or when you drive along in the community. You can see rotational landslides, translational landslides, block slide. Probably you see more rock falls when you drive along the cliffs. You can see the warning, right? Also, you can see some of the net try to block some of the rock falls. So toppling failure and debris flows. Sometimes they just flow like a fluid, can cause damage to the property along the way, and so on. All right. So for highway administration, they are more interested in road pavement, and the bridges, all these assets in the past. Since 2013, people realize more in terms of geotechnical asset. It includes cut slopes, the roadway always cut through some natural slopes to build road. And it can also backfill to build embankment, to build road on top of that. In some cases, you have to modify the ground. Certainly, you might have seen the retaining walls along the roadways. It tried to prevent sliding potential failures and so on. And construction subgrade, it's also part of geotechnical asset because they can use different soil types suitable for the subgrade of the road construction. You can see more regarding geotechnical asset management. Now, each state start put more effort into the geotechnical asset management. All right, you may have seen, some of you may have seen that USGS developed uh, landslides inventory. They have dealing with geohazard and other mappings for a long time. This one just shows historically all these landslides that have occurred. Recently put more effort, look at susceptibility. It means not necessarily all the location have observed landslide, but they have high potential for failures. You can see East Coast and West Coast, especially Rocky Mountain area, approaching mountain range area. You see high potentials of failure. USGS are continuing their effort. Uh, if you have attended AGU, they have several sessions on their work on landslides. NASA also have made effort to develop global landslides hazard assessment model uh, based on their global precipitation measurement uh, data set to assess the landslide hazard because most of landslides are related to precipitations or are triggered by the storm or by precipitations. Our program has been supported by University Transportation Center. US DOT has established UTC program since 1987. It was mandated by Congress. It awards and administers grants to consortiums of colleges and the universities across the United States to advance the state of art in transportation research and technology and develop the next generation of transportation professionals, so workforce development. It has total 35 centers, 5 national. Our program is a national UTC center for safety 21. There are 10 regionals and 20 tier 1 university level centers. UTC Safety 21 is led by Carnegie Mellon University, Dr. Roger. It also has Zhuping and Ohio State and community colleges are UT, Rio Grande Valley, and Morgan State University. Our project is one of the overall programs. There are many projects funded by this program, the Safety 21 program. Ours is to improve highway safety by reducing the risk of landslides. As you see, this National Center, UT Center, is focused on the safety of transportation. The objectives of our project is to assess risks of landslides by integrating physical and AI machine learning models for highway and railroad. You all know landslides can happen in different locations, not necessarily always on the road, but our study is focused on the roadways. We identify, map the high risk area. Again, it's that not necessarily all happen. We are looking for the potential failures using remote sensing data, INSA and LiDAR data. We design and test protocols for real-time monitoring at the select sites in consultation with State Highway Administration, recommends strategies for reducing the risks of landslides for real-time monitoring, and for the high-risk area, also improve the safety of the transportation infrastructure. In some cases, we may also recommend potential modification of the design standard. This one shows a research framework. We try to integrate geomechanics analysis with AI machine learning approaches. So in the central, you can see that eventually we will develop a landslides warning system using the GIS platform. Now on the right side, that's what current Maryland DOT already built some database and information system we can use to eventually establish the final product. They have looked at slope inventories and precipitation data. Currently, we are working with SHA is look at incorporating precipitation data into the geotechnical asset management. So you can look at the precipitation data from NASA and other sources, and also we may look at the flooding area. It could potentially cause erosion and slope failures. We try to look at using machine learning approaches to incorporate into precipitation data, slope geomechanic properties into the system. Eventually, we deploy a dashboard to send warnings, alert to state agencies for timely maintenance and potential response for disasters. I'm going to share some research highlights from what we are currently doing. I will focus on the first one, even though we have more activities ongoing. So the first one, we integrate a hydrologic model and the GIS-based model to map rainfall-induced landslide risk. One of my students is currently working on. The second one is the effort we are currently taking is to work with State Highway, incorporate precipitation data into the geotechnical asset management. We are using part of data as the first in the first task too. The third one is identification of slope failure using LiDAR and INSA images. It's in progress. Kopia Dr. Olabi is advising Bayer Oludi, and they are ongoing. And the last one is a prediction of landslide risk to improve highway risk using Trigger's approach. It's a USGS model. Dr. E. Liu is advising Sami Padepi working on that. So for the first topic area, we are trying to integrate the hydraulic science and geotechnical engineering for landslide prediction. That what is currently in our research. So traditionally or conventionally, hydrologists tend to focus on broader water circle and tend to simplify the geotechnical perspective in unsaturated zones. But on the other hand, geotechnical experts tend to focus on soil mechanics slope stability, especially for landslides assessment and also slope stability analysis. We tend to simplify the complex hydrologic process to, make a judgment call and assess and also design criteria. So in order to integrate, we try to use physical-based model to integrate both hydrologic process and geologic mechanic behaviors into one integrated system. I will explain a little bit more later on. Here, this fourth attempt is to use the physical model, SWOT model, soil water assessment tool model, some of you may know, and it was developed for agriculture for watershed management. Here we try to integrate the soil water content infiltration, so to consider the landslide risk prediction. Integrate the geomechanic model after we simulate the watershed. All right, certainly we need to know what happened. So the map on the top shows the historical landslides we had compiled for State Highway Administration. Not many, but we know we're missing more. But here shows some concentrate area in the middle. So you can see here, it shows different counties. Prince George County and the Baltimore County tend to have more landslides. So when we select this site, this is and the Acacia watershed is primarily covers the Prince George County. The other thing we notice, as I mentioned earlier, precipitation is one of the major factors. So over the history, you can see the bottom one shows the number of landslides. The top one shows the precipitation. You can see 2011, you have high numbers of landslide. It kind of correlated high precipitation year. And again, 2018 is even more clear, but let few slides, but still higher than the average. So precipitation is one of major factors. I'd like to ask a question here. If you like, you can share your thoughts about the factor of the precipitation. What do you think? How many, what the percentage of the landslide might be triggered by precipitation or related to precipitation? Is a 1/10 of them, or let's say 10%, or 50%, or 9 out of 10 landslides are related to precipitation? I'll leave it to you if you want to share. I can tell you the answer later on. Here shows geotechnical asset inventory. SHA has made. Here shows the earlier record. We have a new coverage now. I don't want to overwhelm. They have over 10,000 slopes inventory around the state. So it means you will see more along the highways. And in general, they only covers the 10-foot higher slopes, even though you see much higher slopes. But this is the ground or the base for future assessment of the risk of landslides. Okay, a SWOT model, I said earlier, it's a watershed model. We use it to simulate rainfall infiltration and runoff in Anacostia watershed. We calibrate it, and also we're going to use the GIS to map the minimum amount of infiltration. That's what we need, one of the parameters we need to assess potential failure of the slope. And certainly it needs input data, soil properties, topographic data, and so on. To calibrate the model, we need use the gauge station data, observation data. Now that's one of the challenges. We don't have many gauge station data. So in some cases, it could limit our capacity. And that's one of the challenge we are facing. So we are exploring alternative methodology to better predict landslides. The fundamental equation is basically in out. The water content should be balanced. You have precipitation, you have the runoff and evaporation, and groundwater recharge or discharge. Then the water enter the soil, exit the soil should be balanced. And if there's surplus, then water storage in soil will be increased. It means it could potentially increase the water table in the soil. It create high risk for slope failure. Otherwise, it dry up. The slope become dry. That can is stable. But from the watershed simulation side, you look at what water moisture content is available in for vegetations, for agriculture, and what lateral flows into the streams. It can change the hydrologic condition in the streams. That's why we use the gauge station data to calibrate the watershed water balance. All right, so the model has need to import from daily weather data, precipitation, temperature, winds, and solar energy. And it also look at the DM, the topographic informations, land use. We need, again, last one would be the stream flow gauge station data, flow data, to be used for calibration and the simulation. All right, we try to incorporate by using the watershed model simulation data to assess the physical behavior of the slopes. So one of the equation here we are showing is the safety factor. When safety factor equal 1, the slope is in critical condition. Certainly, they cannot hold below 1 because it's already failure, theoretically. Now, in the field condition, may not be ideal to what the equation tells you. It may, your Fs equal less than 1, slope may still be stable, or even your Fs greater than 1, it may fail, okay? But theoretically, that's the critical condition to determine the slope failure. So we, based on mostly in the Miklovsky's early work to develop this relationship, look at the critical height of the water we need to build up in the slope. And then back calculate how much precipitation we need in order to trigger the slope failure. It means lower values, it can trigger the slope with low intensity precipitation or storm event. If high value, it means more difficult to trigger it because one rainstorm event might only accumulate very low infiltration water into the slope. So it means if the value here, infiltration minimum amount of infiltration water is lower, it means can be easily triggered by any event. If it's higher, it needs large event to trigger the failure. All right, so certainly slope instability, physical model needs all these physical parameters, cohesions, and fractional angles, porosity, and field capacity, and specific gravity. So again, the slope geometries depend on DEM and overlay with physical property. Then also historic landslides inventory help us to verify the physical model simulations. Again, we are looking for critical the precipitation depths to trigger the landslides. Historically, or previous studies tend to have challenges with the thickness of the slope. So we did have an example for a specified Z, but by incorporating topographic wetness index, we can vary the thickness of the slope. It's no longer a fixed number, so it can change depending on the slope stability. So Z is one of the factor we are looking for. Now with the TWI, and also we with the field observation and analysis, we also find it there are some relationship between the thickness and topographic wetness. So with these parameters introduced, we can identify variable thickness of slopes to determine their critical infiltration amount needed to cause the failure. Well, results shows the model has good calibrations. I'm not reading all these criteria, but it shows three indicator coefficient shows very good simulations. So based on the current conditions and the current simulations, the SWOT model was calibrated to a good condition. So it can produce good results in terms of watershed hydrologic conditions. And here shows the top is the precipitation. The right side shows the precipitation from 0 to 80 millimeters. And then left side shows the discharge about the change of the soil water content. It demonstrates the infiltration thickness we are looking for. The bottom figure shows the precipitation on the top. At the bottom shows the surface runoff. That's the watershed simulation. So water we go to the springs or can run off or the infiltrate water. In general, it go to the groundwater. There are some lateral flows. Okay, so with landslide, because our interest is to locate potential site for landslides or failures based on the precipitation, based on the infiltration. Historically, we're assuming 100% precipitation. We go to the slope. That's not the case. We know the precipitation will become runoff and infiltration. So that's our major contribution here. So look at more closely what infiltrate water cause the failure. We tried to look at some of the sites based on the risk assessment and also identify the historical landslide. It shows, you can see the simulation shows the high risk area and this historic failure site. That's just one of the case here. We're assuming thickness of 3 meters of the 1 meters, 3 feet, but we can vary, now we can vary the thickness to match what real condition is. All right, so with theta, as I said earlier, we can see the variable z values or thickness of the slopes can be incorporated into the assessment of landslide risk. Now here shows two events between December 15 and December 18, where the landslides occurred, and you see the high risk area and matches what's historic. The black dot is historic landslides, and red is assessed the risk of landslides. All right. Well, so in summary, we understand there's a critical need to accurate or better assess the risk for rainfall-induced landslides. So far, we have tried the study approach here. Use a SWOT model to assess the hydrologic conditions in the Cassia River watershed as an example here. We try to integrate the SWOT outputs with a GIS-based slope stability model to have better understanding of slope instability and potential landslides at different locations under different conditions, especially precipitation triggered. Now, I'm not sure if you tried or not, because I can't see the chat. 9 out of 10 slides are related to precipitation or storm event, and so. Now, some of the area we see more pipe failure, especially in the urban area. The failure of a pipeline triggers landslide, but it indicates the moisture triggers, even though it's not a rainfall event, but it is triggered by water. So just keep this in mind. Our recent studies catch some very interesting phenomena. Some of the failure may not be in the rainy season, why they are happening. So that's what we're going to explore. Next step, use a different machine learning method and different data available for better simulations. So from our current study, we realize detailed hydrologic modeling are essential for slope stability. As I said, 9 out of 10 are water related. So we need to know hydrologic conditions within the slope. SWOT model has good capacity in terms of look at surface and subsurface uh, flows, but it has some limitations, as you must see in next several bullets. But it has good potential for specific watershed or specific area to look at hydrologic and geotechnical process interactions to better understanding the mechanisms of failure. Again, our study help us to test the geomechanical model integrates with hydrologic processes. Try to identify the infiltration instead of just precipitation itself. Look at infiltration water that triggers the failure. SWOT model does have some limitations in terms of the calibration, it's time consuming, and also scalability because it takes time. Every time you build a model, you need to restart from reconfigure. So it demands high amount of resources, efforts. All right, future work. We are in the process to continue expand the scope of work. The first one is to use satellite images to develop a model for soil, surface soil moisture, then integrate with rain emptying equation to estimate the infiltration better, simulation with some machine learning model. Then once we have that, then we use the physical model I just explained earlier to look at the slope failure related to the soil moisture. This is more scalable so far. I think a more effective way compared to SWOT model. And eventually, we're going to use the machine learning model incorporated to assess the landslide risk, the map potential slope failure area and high risk area. So that's why we can send alert, a warning to the state agency for maintenance, for potential failure, preventions, and so on. All right. Now, as I mentioned earlier, we find some very interesting phenomena. You can see high moisture here. You can see my mouse here, but we don't see precipitation, very high precipitation. So that we also observe it at the location. Now, pay attention to that because precipitation is at airport, not very close to. That's one of discrepancy, but it's kind of off season. We need to look at what really triggers high moisture content or may localize precipitation. Again, you can see off season. It's not monsoon season, but you can see high moisture and where the slope failure occurred. All right. All right. I'd like to thank all the sponsors, UTCs, certainly State Highway, and we also received additional National Summer Foundation just started this year. Certainly our program here, cyber training, and Morgan State has Center for AI and machine learning systems. I'd like to thank all the collaborators and my co-PRs, students, especially students, for their contribution. Thank you all for your attention. Any questions? I'll be happy to entertain.
Thank you. Thank you, Zhuping. So you can unmute yourself if you have a question. Probably we have about 5 minutes, 2 questions. Okay. And actually some students has answered your question. They predict 70%.
Okay.
Yeah, 70 or 60% was caused by the precipitation.
Oh,
Yeah.
that's great.
Okay, it's close enough,
Yeah,
right?
that's great. 8 to 9 out of 10. Yeah. That's
Okay. While we are waiting for others, I have one question. So you mentioned about AI in the future of using AI. And do you think that AI can actually replace the traditional hydrological model approach or the SWOT model you have mentioned, or you are trying to combine both the geophysical model with AI? So can you just discuss a little bit more on that?
that's a very good question. We are on campus. We are debating, AI for teaching researchers. I definitely encourage students to use AI and the machine learning algorithm in their research work. But AI has its strengths. We have to use it. Especially with all the advances recently we are gaining. That's a great tool. We have to use it to their great potential. But on the other hand, the models has advantage too. How we design these models. Now, eventually, AI may try to use this existing model in their database or simulations too, or logic. It can be integrated, but uh, I I don't think they're going to replace it. uh, so hopefully, students understand that. So we do have some of the challenge area, how students use it, and try not to replace your own work with AI and really count your contributions. Well, thank you. That's a good question. I still hope,
Has been discussion like AI almost can do everything nowadays, but it do has many limitations of a
Yeah.
bias, the ethical issues, and so okay. Any other questions from the audience?
Yeah, Dr. Zhang, can you hear me?
Yes.
Hello. Yeah.
Yeah, I just want to say thank you to Dr. Shen because I really love this topic. I the hydrologic model is something I learned a lot before I came to Tamil at undergrad at Auburn, like there's many different model, traditional model. And I mean, from my own perspective, I mean, just my quick idea. I think I think I'm thinking about like taking advantages of AI to make it easier to, I mean, do all the hydrological modeling, so more students won't take too much time, and even outside the department or discipline, and they can also give a try to develop a new tool, make it easier, and can do interdisciplinary research. And I mean, that's the way I'm thinking about. But anyway, thank you for this outstanding presentation. I mean, refreshed my mind, and this wonderful. And thanks again, Dr. Shin.
Thank you,
Thank
Oliver.
you.
Okay. Any other questions? Okay, if not, let's give our biggest thanks to Dr. Sheng, and thank you for your inspiring presentation. And if you have more questions for Dr. Sheng, please feel free to email him or also contact me. And I hope everybody have a great afternoon. And thank you for attending
Thank you very
the
much.
webinar. Okay, bye.
Bye.
Bye, everybody. Thanks, Dr. Jiang. Thanks, Dr.
Okay.
Shin.
Thank you so much.
Thank you, Zhuping. Bye.
Bye.